Starting off the sessions this afternoon is Lindsay. Lindsay is not a psychologist, but he will be talking about the psychology of alert design.
Thanks. I think that was a very suitable disclaimer. That's very true. I'm not a psychologist. My name is Lindsay. I'm from Sydney, Australia, just outside of Sydney, Australia. I'm Oxesis on Twitter here. So I'm actually an engineering manager at a managed hosting company called Bulletproof. You may be familiar with some of my work, Cucumber Nagios, Visage, and Flapjack. Flapjack, which is quite relevant to this talk, in fact. All right, let's begin. So on January 16, 2003, the Columbia Space Shuttle took off, and as it was taking off, there was a small amount of foam debris that came off the main rockets, and it did what's called, what in NASA terminology they call a foam strike. And this seems like a fairly innocuous sort of thing, but when you have a small chunk of polyurethane traveling at 850 kilometers an hour, it tends to leave a fairly large hole in the underside of the space shuttle. And this is part of the heat resistance that allows the space shuttle to re-enter the atmosphere. So fast forward to February 3, 2003, the space shuttle started re-entry.
And Columbia, Houston, we see your tire pressure messages and we did not copy your last.
Roger.
Can you guys hear this okay? Yes? No? Hands up for yes? No. Hands down? Oh, hands up for no. Okay, sorry. So the static that you can hear possibly there is the radio equipment cutting out. Ground control has just asked about a bunch of alerts that they've started receiving on their consoles. And they're in the process of re-establishing, or attempting to re-establish radio contact with Columbia as it's re-entering the atmosphere.
Columbia, Houston, UHF comm check.
This is the flight director. You see them all gazing intently at their monitors. I'm sure you've been in a similar sort of situation before, when some massive disaster is unfolding in front of you.
Columbia, Houston, UHF comm check. Columbia, Houston, UHF comm check.
Unfortunately, while that was unfolding, this was happening outside. This is captured on free-to-air television. Not a good ending for anyone involved, as you can imagine. 7 astronauts killed. So let's ask a potentially facetious question. Did NASA have good alerts in this particular scenario? And more importantly, what actually constitutes a good alert? And I posit that a good alert is actually more of a moral judgment than anything else. Nobody actually sets out to create bad alerts, right? The alerts are designed in context, based on the situation that people are in. And that context is locally rational for the people that are operating in it. And so from a psychological perspective, local rationality is this concept that people make what they believe to be the best decisions based on the data that they have at hand. Obviously, the data that they had at hand was not fantastic. So we design alerts for humans. Let's try and take a few moments and actually get a better understanding about how humans think. So I posit there are actually really just 2 principles that you probably need to apply when you're thinking about alert design. Firstly, don't startle the operator. And secondly, don't suggest what the problem might be, just to expose the information and allow the operator to draw their own conclusions. All right, let's take a step back. What is a cognitive bias? Well, firstly, a cognitive bias is a mental shortcut. And what that does is it basically, your brain is constantly optimizing for timeliness over accuracy. So if we look at it like sort of traditional problem, not even traditional, just normal problem solving, sorry, that your brain is doing on a daily basis. You've got some problem solving that you're doing, and your brain is applying some sort of heuristic to that, and if it produces a correct result, we say that this is a rational choice. Then, in another scenario, you're doing problem solving again, you apply the same heuristic, maybe it's another heuristic, depending on the circumstance, and it results in an incorrect result, and this is what we call a cognitive bias. Very, very simple. And there are a whole bunch of cognitive biases that affect the way that we react to alerts. So just very briefly as well, like we're probably all familiar with what a heuristic is, but in a cognitive sense, it's about pattern matching. And these things are actually really important. These are the things that actually helped your ancestors survive. It's actually probably part of the reason that you're actually in this room today, and that they survived and thus you were here. All right, so a little bit of a case study of a cognitive bias. Who can tell me what is significant about this date? Anyone? All right, perhaps this airport is a runway. Familiar to anyone? What was that? Not quite. This is Tenerife on the Canary Islands. So I don't know if you're particularly familiar with what happened at the Tenerife disaster, but it's actually a really interesting example of human psychology and cognitive biases in particular in action. So the situation is quite simple. There are two aircraft that were leaving the airport. They're both Boeing 747s. One was a KLM flight, the other one is Pan Am. They're both communicating with the radio control tower. The KLM aircraft trundles down the down the runway. The Pan Am aircraft is going down the taxiway. They both end up in a position where they're actually facing one another on the same runway at the same time due to a series of miscommunications between the Pan Am and the KLM flight and the control tower. And both aircraft at the same time start taking off towards one another. Sounds pretty ridiculous, right? And so this was the result of that. So on the KLM flight, 234 passengers and 16 crew were killed. What happened is that the KLM pilot noticed that there was another plane coming towards him. He had slightly more speed than the Pan Am. He tilted the nose back as far as he possibly could, tried to take off. As he was taking off, he clipped the undercarriage and one of the jet engines on the Pan Am flight, which caused him to basically lose complete control of the aircraft. The aircraft descended 500 meters into the air and then nosedived towards the ground where it exploded on impact as it was fully laden with jet fuel. Pan Am flight, though, is really, really interesting. So not a whole lot of people were actually killed in the initial impact. So there was severing of control lines from the cockpit. But the aircraft basically trundled down the runway with a significant amount of damage to it, and it stopped about 1 kilometre away, about 800 metres or so away. And there are a lot of people that survived that, but of all those people, there were a huge number of them who were actually just frozen in place, weren't reacting, weren't doing anything in that situation. So this is a fantastic case study of where the normalcy bias comes in. So the normalcy bias is actually two things. Before a disaster, humans are prone to underestimate the risk to themselves, the effects of that disaster, and the preparation required. And the reasoning is that, well, because something bad has never happened, it never will happen. During a disaster, the normalcy bias rears its ugly head again. So your response, you have slowed and delayed reaction to stimuli. You try to seek validation from the other people around you. You tend to ask people about 4 to 5 times before you actually start acting on that information. And you have an optimistic interpretation of the events as well. I don't actually, it's not really possible that something here could be wrong, so I'm just going to assume that everything is actually completely normal. And then when you're faced with these sort of situations, there are these common reaction steps that everybody goes through. So the first one is cognition, perception, comprehension, decision, implementation, and then finally, movement, where you actually go and do something. Your brain is doing all of these things before it even gets down to taking some sort of action based on the stimuli that you've just become cognizant of. These are all complex tasks, complex cognitive tasks. There's no way that you can actually skip over any of these. You can practice to make them more automatic, though. And the problem with that is that people who don't practice those deliberate during that disaster, so they're all going through those 7 steps that I mentioned just a second ago. So in the Tenerife case, 70% of the people that were survivors froze, 15% freaked out, and 15% reacted to the situation that was at hand. So there's a great example of a man who was on the flight, and he was one of the 15% that reacted. He was sitting next to his wife, who was one of the 70% who was not reacting. Basically, he stood up, shouted at her to get up out of her seat. She moved. She wasn't really aware of what she was doing, but she was moving. She managed to get out. But of those 326 people that perished in that, a vast majority of them were just sitting in their seat, waiting to accept their fate. So to be a little bit flippant about this, no practice equals a higher mean time to recovery or mean time to response. So it's pretty important then when we're designing these sort of monitoring systems to not startle the operator so that the normalcy bias doesn't kick in. So a really simple way to do that is to drill and then dampen or limit the number of interruptions that we are interrupting the operator with. So speaking of interruptions and your ability to look over information really, really quickly in a rapidly evolving situation, this is a test. What I need you to do is I need you to read the following statement once. This should be interesting actually because you get different results depending on the language abilities of different people in the audience. Actually, quick show of hands. Who here, they consider English to be their native language? Okay, great. And who would say they are not native English speakers? Okay, this will be very interesting. Science in action. So what I want you to do is read the statement once, and I need you to count the number of times that you see the letter F. Okay, the statement is going to appear in this box. Don't fuck it up. Go. Okay, that's it. How many times did you see the letter F? So raise your hand if you saw it 5 times. Okay, raise your hand if you saw it 6 times, 7 times, 8 times, more than 8 times. Okay, so the correct answer is actually 8. How confident does that make you feel about your ability to respond to large numbers of stimuli in a highly stressful situation, or even a partially stressful situation? Hopefully I'm a nice guy. And this is an underlying psychological thing. It's a heuristic that drives a lot of these cognitive biases called the fluency heuristic. So your brain is focused on looking at particular words, and it tends to ignore a whole bunch of other words that it doesn't think are actually relevant to the task at hand. So specifically, your brain is looking at patterns. It's looking for large words. It's looking for nouns, pronouns, adjectives. And it tends to miss words that are small, that join other words. So, it's looking for that pattern. It expects to see that pattern continue, but it's skipping other information. Specifically, we're seeing the off there. Right. All right, let's look at this from another perspective. Let's talk about modeling failure, or what failure looks like in a rapidly developing situation with lots of complex infrastructure in play. So the traditional way that we tend to look at this is that you have system A, which is influencing this other system, system B, and that's causing some other action on system C, and again on system D. which eventually results in some sort of horrible disaster. These can be a combination of technical systems and social systems as well. So the traditional response to that, and the very typical software engineering response that we're all guilty of, is that we want to add barriers here. We want to add barriers between these different layers. So we've got all of our different things here, and just before it gets to the boom, we're going to throw in another layer, another barrier. And, you know, what the hell, let's just throw in a few more barriers as well while we're at it. Okay, so what if the thing that caused that explosion, actually, sorry, and those barriers can be a combination of hard and soft. So hard being like an actual technical limit in a system, and soft being some sort of human process, some sort of standard operating procedure. So what happens if you have D actually go via E, this other system that you didn't really think of in the first place? It results in some sort of catastrophic failure. So obviously the thing to do here is to add more barriers. Ooh. Okay, so let's add some more barriers over here, because C led to F, led to E, led to boom. Crap. So obviously we need to add more barriers to that, right? And then, you know, the system is sort of a little bit dastardly. It's a little bit cunning. It keeps working around all these barriers that we keep implementing. And look, it's gone all the way through there, and it's managed to get down. That's a bit of a pain. So let's put in some more barriers here, right? And then, before you know it, you've ended up with this massive, complex interweb of dependencies, and then a whole bunch of barriers to go with those as well to protect every system from every other system that's around it. Right. So this sort of modeling, sort of static modeling of things works really, really well when you have systems that are, by definition, static. But turns out that we don't really live in that world anymore. We actually tend to work more in dynamic systems where things are constantly reallocating. So all those barriers that you just defined, well, they may not actually be that useful anymore. Well, the dependencies that you just set up in your monitoring, your parenting and whatnot, maybe they aren't actually as relevant. And of course, your failure as well, that's like, we're looking at a really, really simple scenario. The failure and that explosion is going to be transient. It's going to move all around your infrastructure, whether you like it or not. And so this is like a textbook definition of complexity, right? And there's a whole body of science that's dedicated to looking at this. So our systems themselves are not actually static. Our systems are dynamic, and the accidents that we have, the incidents that we face, come from the relationships between parts, not the actual broken parts themselves. So I'd like to posit, does it actually make sense in this world to keep using the concept of parenting? Maybe yes, maybe no, it depends on the circumstance, right? But the problem with parenting is that it does require a hell of a lot of work. It assumes the system is static. And unfortunately, whatever definitions and relationships you're setting up there are probably going to become rapidly out of date as well. What about emergent behavior? Unseen interactions between different things that, you know, reverberations through the system. So for example, you have this one little component over here, component F, and it's going to start vibrating, and it's going to bump up against other components, you know, just little gives and takes in the slack within the system, until eventually you have a small explosion, which then cascades and causes a whole bunch of other explosions as well. But it's all good because this thing over here is alerting. That was the thing that was alerting first. That was the thing that was failing first, right? So the problem with this is that, you know, we're trying to codify these relationships into our monitoring system. So going back to my point that I made before, let's try and not suggest what's happening within these complex systems. Let's expose the information and allow the human operators to draw their own conclusions. All right, let's look at some other industries. So aviation, AF447, Air France 447 that crashed into the Atlantic Ocean between Rio de Janeiro and Paris. So there's a huge recovery operation there that took about 3 years and cost a lot of money, like I think about 500 million. You know, don't quote me on that. It costs a lot of money. And in that time, there were 70 stall warnings, and this is the fact that the media really seized on when they were doing their reporting about this particular incident. So, sorry. These two things here, you know, we'll just skip on because that slide won't render. You know, they should have reacted, is basically the response from the media and when looking at the result of what happened. But it turned out that there was actually a lot of things that were happening in the cockpit in the 14 minutes prior to the aircraft pancaking into the ocean. So specifically, there was an autopilot disconnect, which was an audio alert. There was an alternate law reconfiguration. So this is a mode that the flight control computer is operating in. And when it switches between normal law and alternate law, you get these funny little side effects like the plane is suddenly able to stall. Oops. And then, of course, you've got the stall warnings, the thing that media picks up on. There was this, 70 stall warnings. And the stall warnings, I believe, lasted for approximately 52 seconds. So, how could they possibly ignore that information? C-chord altitude horn, which is like a cavalry charge, a very, very loud and somewhat disorienting noise that's meant to attract the attention of the operators of the aircraft that, hey, we're actually falling through the sky. And then on top of that, because the operators are so overloaded with all the information, all the stimuli that they were receiving, some operators were pushing down on the stick, other operators were pulling back on the stick. The plane made that apparent, very apparent, to the operators by showing a small little light on the dashboard that, hey, there's actually two people operating on the same thing at the same time doing completely opposite actions. So if we sort of put this into a checklist, right, 4 oral stimuli and 1 visual stimuli, and it's pretty obvious to see that they were completely overwhelmed by feedback. And the great thing about the BEA report, which was the French task force that was designated to investigate what happened, was this particular quote. There's a possibility that the crew did not identify the stall warnings purely due to the amount of oral stimuli. All right, let's look at another context, operating theatres. So John Allspore linked this earlier this year. It's a pretty interesting paper. So it was actually a study that was done in 2010. It was actually just done up in Hamburg, so not too far from here. So there's a bunch of medical equipment. It was a controlled study where they basically looked at the number of alerts that were generated during cardiac procedures. So there's a bunch of monitoring equipment. The one thing you can never discredit the medical profession on is their love of monitoring. They've got monitoring absolutely everywhere. So plain old patient monitors, anesthetic monitors, pulse oximetry, ECG, arterial blood pressure. This thing is really, really painful. And then just a central venous blood pressure as well. Had 1 second sampling. And on top of that, all of the procedures were actually video recorded as well. And what was the result of this study? Well, on average, they received within each operation 1.2 alerts per minute, of which 80% of those had absolutely zero therapeutic consequence, didn't guide the way that the surgeons or the staff or any of the nurses or anything like that were responding to the situation, the cards that they were dealt. And if that wasn't bad enough, 30% of those were false positives. If I had a monitoring system for my complex IT infrastructure that had 30% false positives, I think I'd probably just turn it off. All right, so let's look at how we can actually improve, looking at what these other industries are doing, looking at all these different psychological underpinnings. Let's see if we can actually make something happen. So the first one is to provide more context, and that's not to say that you overload the operator with huge amounts of data. You try and provide what is more relevant situational information to them. So here's a really simple example for, say, an Argios plugin, right? It's possibly a little bit small for the people on the back, but we'll zoom in a little bit. So this is basically querying collect D, and it's taking the standard deviation of a bunch of data, a sine wave basically, and it's providing some very simple output to the operator here. So it's saying that 40% of these are outliers or outside of the standard deviation. It's explaining why the monitoring alerters are firing in the first place, what the actual expected static threshold is. And then it's providing just a really simple textual graph. I'm not quite sure how PagerDuty will sort of explain this over the phone. It'd be quite funny, but yeah, we can provide this sort of contextually relevant information to the operator. And this ties again into don't suggest, explore. Let's try and reduce the notifications, and maybe we can be a little bit more serious in this as well. So no notifications on, I'm going to argue for a second here that maybe one way to solve this is to have no notifications on individual monitoring checks, but you want to do some sort of notification on the aggregate itself. So turns out that there are actually tools to do this already. So there's Check, written by Jordan Sizzle. And you basically run a query against a whole bunch of Nagios state, and it will look at the aggregate state of lots of different services together, and it'll send out a single notification for that. Raymond also has event grouping as well, where they do time-based static windows and that sort of thing, which is pretty fantastic for aggregating numerical metrics from lots of different sources. And this totally plays into this concept of not actually startling the operator. Let's look at rollup for a second. So all we want to do here is just limit the alerts that are emitted. And we can do that by aggregating alerts together. So it's a really simple way that you can actually start implementing now without actually changing any of your tools. It's actually more of a process change. So when you have a large incident, turn off your monitoring, or at least turn off the notifications from your monitoring. Definitely keep your monitoring running in the background. Use it as a diagnostic tool. Definitely don't use it as an alerting tool. And if you want people to watch it, then you want to try and limit the number of people that are watching those alerts and graphs. Don't necessarily know how effective that will be, but it's better than having everyone poring over all of this data that's evolving in real time. One of the other ways you can look at it from a technical system perspective is try and do smarter alerting rollup. So there's a little project that I've been working on for a little while now called Flapjack, and core to the concept of Flapjack is delay-based notification. So we don't actually notify based on the number of times we've seen something fail. We do it based on how long something has been failing for. And the reason that we do this is that we actually end up with a buffer of events that we can then start performing operations against and aggregating together when we want to send out the notifications. And building on top of that, we are in the process of implementing per media rollup thresholds. So, for example, for SMSs, you probably don't want to receive many, you don't want to receive SMSs if you've got more than, say, 10, even 5 things failing simultaneously. I mean, SMS networks these days are pretty creaky and probably going to start falling over pretty quickly. For Jabber, for XMPP, for example, you might, you're probably okay with huge amounts of data going through that because you can silence that pretty quickly. But you might still want some sort of roll-up, say 500 things failing simultaneously. You probably just want to send a single notification for that. And then you have other systems like PagerDuty as well, which already do fantastic roll-up. So in which case you just want to pass all those notifications straight through. This is the sort of stuff that we're trying to do in Flapjack today. And this totally plays into not startling the operator. So then we have granular alerting levels. Finally, so Alerter from The Guardian is really, really interesting. One of the things that they've tried to introduce is the concept of multiple severity levels, beyond what Nagios actually provides, right? The problem with these very simple, well-defined alerting levels and severity codes is that you tend to find that systems aren't just going to be in a state transition directly from okay to warning to critical to unknown or anything like that. There's going to be a slow drift from one state to another. Prioritizing that information makes it easier for the operators to be actually able to deal with that. And this is really important as well because, if you look at the way that we do this sort of stuff in Nagios right now, we tend to alert, when something has actually crossed this threshold, whereas maybe we actually want to try and notify when things start bouncing around within our complex system. So the good news is that it is not all doom and gloom. It turns out that in IT, we're actually very much on the cutting edge of what we're trying to do when it comes to alert design, especially when you consider the 80% of alerts in these sort of situations that have no therapeutic consequence, or overloading and operating with a huge number of alerts, which doesn't really cause, is a contributing factor to them plowing the plane into the ocean. So we really need to hold true to these two principles of not startling the operator, and don't suggest, expose information, allow them to draw their own conclusions. We are designing alerts for humans. Let's understand how humans think, and maybe we're able to look out the window at the problem from a slightly different perspective. Thank you.